back to the lecture series on pattern recognition. So, this is Josna Devi Bodapati, Assistant Professor, Department of CSE VFSTR. So, in the last lectures, we have discussed what pattern recognition is and what are the various real-time applications of pattern recognition. So, in addition, we also discussed what are the various stages of pattern recognition, and to get the better understanding of the pattern recognition systems, so it is very much important to understand various mathematical concepts. So, like you should have the familiarity of linear algebra, then calculus, and also probability and statistics. So, these kind of mathematical concepts familiarity is very much important. So, to get the better understanding of the machine learning or the pattern recognition systems. So, in this course I will be discussing the vector spaces as part of the linear algebra for the pattern recognition. In this session I will basically discuss why linear algebra is required for the pattern recognition, then what linear algebra is, what vectors are, and what the vector space is, and what are various operations that can be performed on vectors, then what are linearly dependent and linearly independent vectors are. So, what is linear combination of the vectors is, and in addition we will also discuss what are orthonormal and what are orthogonal vectors are. So, they have some special properties. So, in the future lessons we need to understand all these concepts. So, let us start with getting the intuition of why linear algebra. You would be wondering why we are studying this linear algebra, which we already studied in +1 or +2 now. So, but this is very important to have the familiarity of the linear algebra concepts to get the understanding of the pattern recognition systems. So, let me explain briefly. So, why linear algebra is required to get the understanding of pattern recognition systems. So, if you consider the stages of the pattern recognition system or the typical workflow of the pattern recognition system, if you consider, so initially from the real world you need to get the data. So, you can use the sensors or the cameras or the video recordings, whatever it is. So, using some techniques, so you just collect the data from the real world. So, once your data is available with you, you need to apply the pre-processing and the enhancement techniques. So, once you apply the pre-processing and enhancement, so that is now your data is clean, and then you need to apply the feature extraction techniques to get the features from your data. So, from the pre-processed and clean data, so you need to extract the features. So, the raw data cannot be given to your pattern recognition algorithm. So, once you get the features from the data, so then you need to pass it to your pattern recognition algorithm. So, let it be a classification problem or the clustering or the regression problem. So, you had to convert your given data to features, and then only you can pass that to the pattern recognition algorithm. So, that is how typically any pattern recognition algorithm works. So, the takeaway here is, so you need to get the features from your data. So, the raw data cannot be given as input to your pattern recognition algorithm. So, you need to apply some processing to get the features out of the given data. So, let us see what these features are and what feature vectors are. So, features are basically the measurable properties of any given data. Say for example, in the case of the house prediction problem, so in that case whenever you decide the price of the house, so how do you buy a house? So, how do you give the price for a house is, so you will be go for understanding the number of rooms of the house, then what is the size and in which location it is located. So, all these properties will be taking into consideration. So, when you predict the house, right, that is how we do. So, similarly, so for the machine learning algorithm also, so you say for example, if you want to implement this house prediction algorithm, so in your machine, so then you need to give all these as input to your problem. But the problem here is this cannot be given as input to the algorithm directly. So, first you need to apply some feature engineering. So, that is you need to convert that to features, and then only these features can be given as input to your machine learning algorithm or the pattern recognition algorithm. Basically, to achieve pattern recognition, you will be applying machine learning algorithms. So, to the pattern recognition or the machine learning algorithms, the input is the set of features. So, what is feature vector? Feature vector is the set of features. So, if you consider each of these, so this is a property and this is another property and this is the other property, right. So, these are called as features. So, features are the measurable properties of the given data. So, in this case number of rooms is one particular feature, then size is another feature and location is another feature, right. And if you consider all these set of features, then that set of features can be called as a feature vector. So, for example, how do you represent a particular house in this house prediction problem is, so the number of rooms, number of bedrooms, then the location and the number of basement rooms. There are no basement rooms in this example, so it is -1, right. So, these are all the things that is combined, we can call it as features. So, this raw data whatever we are capturing from the real world, that cannot be passed directly to the machine learning algorithm. So, what you need to do is, so you need to convert that to feature vectors, basically into the numerical representation. So, let it be the number of bedrooms, number of rooms or the location. Basically the location is a text here, but even then it has to be converted to the numerical representation. So, and then it can be the set of features in the numerical representation that can be passed to the machine learning algorithm. So, the takeaway here is, so given the raw data, basically from the real world you are collecting the data and that data is called as a raw data, and that has to be converted to the whatever the type of data you are collecting. So, let it be speech, image or text, whatever it is, you need to convert that to the numerical representation. So, typically, so this is called as a feature vector, and these feature vectors forms as the input to your machine learning algorithm. And to convert this raw data to the numerical representation, so you need to apply set of processes called as feature engineering. So, the process you are applying to convert the raw data to the numerical representation, and that is called as the feature engineering. So, in the later sessions we will be discussing, so how do we convert and how do we apply the feature engineering. Now, we understand that, so whatever the given data that has to be converted to numerical form, so before it is passed to the machine learning algorithm. So, now various types of data and how it is represented before it is converted to the machine learning algorithm. So, consider the text data. So, now this is the text data that is collected, and here the task is, given this data, so given this text data, you need to classify whether it is a puppy or not. So, that is the tag, the text is quoting puppy or not, that is what the task is. So, in this task, this raw text has to be converted to some numerical form. So, here these are the set of numbers that are used to represent this text data. So, now again I repeat the same. So, whatever the type of text, whatever the type of data you have, that has to be converted to numerical form, and then it has to be passed to the machine learning algorithm. So, let it be the text, let it be of any type. So, this is how the text is converted to numerical form and then it is passed. So, again, so you can use any set of techniques. How do you convert this text data to numerical form? So, there are a lot of techniques. So, you can apply any one of the technique and you can get this conversion done, and then you can pass that as input to your machine learning algorithm. So, now consider the image classification problem. So, given this image, so the problem is to understand whether the image is representing a person or an animal. So, that is what the task is. In this case also the input is an image. So, even though it is an image, so you need to convert that to set of numbers. Again, you are representing as a form of numbers, the feature vector is a number, and then you are converting that, you are passing that to the classification algorithm. So, now consider the speech case. The input to your model is, let us consider the problem is speaker recognition or speech recognition. In that case, the input to your problem is speech. Speech is basically an analog signal. So, considering that signal, so you are just splitting that signal into set of segments. Say for example, at 10 millisecond or 20 millisecond frame you are calling it as a segment, and then from each segment, so you are passing to some algorithm, say for example MFCC algorithm which is used to convert the given speech signal into set of numerical representation. So from this segment of speech, I am getting this feature vector and which contains some 40 features. And like that, so you will be getting a feature representation for every segment of the speech. So now from this speech segment, you are getting again another numerical representation. So like this, for every frame, you will be getting set of features. So if you consider to represent this given speech signal, I am using 15 different frames, and each frame is represented as 40 features. So that will be the input to your machine learning algorithm. So here again, the given input is speech signal, and even then you converted that to set of feature vectors, and then you are passing that to your machine learning algorithm. And now consider, so based on the previous discussion, the takeaway here is whatever the type of data you are passing to your algorithm, first you need to convert the raw data to numerical representation, and then only you can pass that to your machine learning algorithm. So let it be the image, let it be the text, let it be speech. Whatever the form of the data that is input, you are required to convert that to numerical representation, and then you need to pass it to the machine learning model. So consider this example. To get the better understanding of why linear algebra is, let's consider this example. So here the task is handwritten digit recognition. So these are the set of images that are given to us, and how do we represent these images? So say for example, each digit is represented using a 16 by 16 matrix, and instead of directly representing it, I will be converting that to a vector. So 16 by 16 matrix, basically the 16 by 16 matrix, I am converting that to a vector representation. So in that case, that 16 by 16 as a vector, I can represent it in the space of 256 dimensional space. So now each image is represented using 256 dimensional representation, so a vector representation. So like that, so if you have more number of images, so the input to the machine learning algorithm is always a set of images, right? So in that case, instead, if it is only one image, I can pass a 256 dimensional vector, but in this case I need to pass a set of images. Say for example, n images I need to pass. Then, so I need to make this stack of vectors as a matrix, and then I will be feeding that matrix as input to the machine learning algorithm. So now the matrix size is of size 256 by n dimensional, where n is the number of images and 256 is the representation for the each image. So now the conclusion is, depending on all the discussion that we had so far, it is very much clear that, so the input to your algorithm, the machine learning algorithm, is a vector or a matrix, right? So it's always your pattern recognition algorithm takes a vector or matrix as input, and inside your model, the algorithm will be processing the vectors and matrices, right? So that is, so you need to have an understanding of mathematical background, so to understand what is happening inside this machine learning model. So that is the reason why you should have the familiarity of the linear algebra, then probability and statistics, and also the calculus. So I hope now it is clear. I justified why I am teaching mathematical foundations as part of the pattern recognition course. Now consider this example of house prediction problem. So each house data is represented as a, so the given raw data is, so number of rooms, number of bedrooms, size of the house and the location. So that is converted as a set of features, and we call that as feature vector, and each house data is represented as a single feature vector, and likewise we have multiple houses. So all the house data is represented as a separate feature vector, and all together they are passed to your machine learning algorithm. And inside your machine learning model, so it's processing the data that is passed as a set of vectors or a matrix. And if you consider the output of the machine learning algorithm is also the set of numbers, right. So basically you need to have good understanding of how do you process the data, the numerical data basically. So that is the reason why we are trying to understand the mathematical concepts that are required. So let's start with the simple concept, the simple mathematical concept, that is linear algebra. So consider the mathematical objects. So mathematical objects are formed depending on the way you are organizing the data. So the amount of data you have and also how you organize the data. So consider if you have only one single number, and that is called as scalar, and if you have a sequence of numbers and there is some ordering in those numbers, then that is called as a vector, and that vector can be of a row vector and a column vector. So a vector is a ordered sequence of ordered collection of numbers. So vector can be of a row vector and a column vector. So if you are representing as a single row, then it's called as a row vector. If you are representing it as a single column, then it is called as a column vector. So then if your representation is a 2D array representation, so then it is called as a matrix. So here if you observe, this representation is having both number of rows and the number of columns, that is a grid representation. So it's basically a two-dimensional representation of data. So such representation is called as a matrix, and if it is more than two-dimensional, basically we call it as a tensor. So if you consider it as a three-dimensional representation, here this is one dimension, this is the other dimension, and this is the other dimension. So we have three-dimensional data. So you can even call this as a tensor where the dimension is 0. So you can call it as 0th tensor. So this is 1D tensor, 2D tensor, and 3D tensor, or basically whichever is having more than two-dimensional, you can call it as tensor. So tensor is the object which is represented in multi-dimensional format with more than 2 dimensions. You can even have 4 dimensions, 5 dimensions, 6 dimensions, even 10 dimensions. So depending on the way you are representing your data, so the names are given as scalars, vectors, matrices, and tensors. So scalar is a single number, vector is a collection of numbers either in a row format or in a column format, and matrix is a two-dimensional representation with set of rows and columns, and tensor means which are having more than 2 dimensions. So greater than or equal to 3 dimensions, you can call it as a tensor. And now let's see what scalar is. So as we already seen, scalar is a single number. So it can be real number, it can be a rational number, it can be an integer number, it can be any type of number can be called as a scalar as long as it is a single number. So and we always represent a single number in a italic form, say for example a, n, x, so on and so forth. And we are very much familiar with the operations that can be applied on the scalars. Say for example, I can say simply, I can say a plus b, where a and b are scalars. We are very much familiar with that. I need not to repeat. So a minus b, subtraction, then the multiplication, then the division, so then the exponent. So all these are the operations you can apply on the scalars. So I am not going into the details of that. So all of us know that very well. And now let me introduce or give a review of the vectors. So what vectors are and what are the various operations that can be performed on vectors, and what are the special properties of the special vectors. So let's discuss that. So a vector is basically an ordered collection of numbers, and basically so in pattern recognition we are more interested in real numbers. So an ordered set of real numbers. So if it is n dimensional, then there will be n set of numbers. So that's what the vector is. So if you consider this vector, so this is the vector, it's basically a column vector, right? So vector means it's a column representation only. So if it is a row vector, then you can consider it as a transpose of this vector. So this is an example for a vector in the 4 dimensions, because this vector is having 4 numbers and there is an ordering among the numbers. So this is the first number, this is the second number, and this is the third number, this is the fourth number. So how do you access the number? So just like how we access the matrix So it's a one-dimensional matrix, you can consider it as. So it's at the 0th index, at the first index, at the second index, and at the third index. So using the index of the vector, you can access a specific element of the vector. So that is how vector is an ordered set of elements. And now consider what is that vector? That vector is exactly, so the transpose of the given matrix. So this is the column vector and I am representing the same as a row representation. So how do I get that? So you just apply the transpose of the given vector. So whatever is there in the column in the same order, the order will not be changed, remember that. So the same set of elements I am writing in a row representation. So that's called as the transpose of the vector. So then you need to understand that, so if it is a vector means it has both magnitude and the direction also. As long as it is a scalar, say for example 10, so 10 means it is only a value with this 10 as a magnitude, right? It does not have any direction. But if it is a set of numbers, then that means it is a vector and it is having both magnitude and the direction. So vector is basically having both magnitude and direction. We will see what the magnitude is, how to compute the magnitude and all those things. So consider this vector, and this vector, this is the starting point of this vector and this is the terminal point of this vector. So consider this vector. For this vector, this is the initial or the starting point of this vector and this is the terminal end of this vector. And if you consider this vector, it is moving this direction. So it is having that direction. And the magnitude of this vector is from here to here. So we will see later how to compute the magnitude of the vector. So that is how a vector is having both magnitude and the direction. And now consider this vector which is in the two-dimensional space. So why I am calling it as a two-dimensional space is, so here this is the vector and it is represented as two values. So I can say that it is a two-dimensional vector. So you can represent it as in the two-dimensional representation. So the x-axis and the y-axis, right? So the x-axis is x1 and y-axis it is x2, right? That is how I can represent a vector in two-dimensional representation. Of course, in the higher dimensions, it is not possible to visualize. That is why I am showing a vector in the two-dimensional representation. And now if you consider this vector, this is a vector in the four-dimensional space. And if you have n numbers in your vector, n set of elements in your vector, then you can call it as n-dimensional vector. So that is how you can say that your vector is of two-dimensional space or the three-dimensional space or four-dimensional space or n-dimensional space. It depends on the number of elements in that vector. And now let us see what the vector space is. So vector space is defined basically, it is a set which is closed under vector addition and also multiplication, scalar multiplication, and it should satisfy all these properties. All the 8 properties are satisfied for a given set of vectors. So then we can call that space as the vector space, the set of vectors as a vector space. So it is commutative, that is given any two vectors u and v. So you can add them in any order. So u plus v and v plus u. So both gives the same results in the same value. So that is what commutativity is. And then associativity. So if you consider associativity, then u plus v plus w and u plus v, when you added that to the result to the w vector, so both result in the same. So we already, we know these rules pretty much, right? So we are pretty much familiar with these rules. Then the next is additive identity. So additive identity is the zero vector. So vector with all zeros is the zero vector. So when you add any vector to the zero vector or any vector, a zero vector to the any vector, the result will be the same vector itself. So the vector zero vector is the additive identity for any given vector. And similarly, so for any given vector, there exists a additive inverse. That is for any given vector v. So if you can, there is an existence of the vector x. So when you add that x to v, then the resultant will be 0. So that is what the additive inverse of the given vector is. And similarly, associativity of scalar multiplication. So consider the scalar C. So C is a scalar and U and V are the vectors. So if you add two vectors and then multiply the result with the scalar, or otherwise, so multiply individual vectors with the scalar and then add them up. So both results in the same value. And similarly, distributivity is applicable for scalar sums. So consider C, D as scalars and V is a vector, and then if you add these two scalars and multiply that with a vector, then that results in the same value when you multiply the scalars separately with the vector V and then add them up together. So that is how distributivity law holds for the scalar addition of vectors. Then distributivity of a vector. So consider now the vector V, distributivity in the case of multiplication of scalars. So C and D are the scalars, V is a vector. Then in this case, first you are multiplying your vector with D, the scalar, and then after that, after getting the resultant, you are multiplying that value with C. So that gives the same result as when you multiply the scalars first and then multiplying that with the vector. So both result in the same value. So and consider the last law, that is scalar multiplication identity. So if you consider any vector V and if you multiply that with the number 1, which is a scalar, then that results in the original vector itself. So this is called as scalar multiplication. One is called as the scalar multiplication, scalar identity for multiplication. So whenever the vectors satisfy all these properties, all these properties are satisfied by the vectors, so that is called as a vector space. Now let's consider this picture. So this picture shows set of two vectors here in this case. Now consider how do we compare given two vectors. So I am given A and B as two vectors, and how do I compare them? So given any two numbers, say for example 5 and 2 are numbers. So I can easily say that, so 5 is greater than 2 or 5 is less than 20. So 5 is equal to 5, right? So I can easily say that because it has only the magnitude. Scalars have only the magnitude. So that is how we can compare them. But given the vectors, how do I compare them? So because vectors are having both the direction and the magnitude. So in that case, how do I compare them? So let's see how do we do that. So here A and B are the vectors, and how do we compare the vectors is, so depending on both magnitude and direction of the vectors. So if both magnitude of the vectors is the same and they are in the same direction, then only we can call them they are equal, otherwise they are not equal. So consider this case. So A and B are two vectors. So if you observe, they are moving in the same direction, right? The direction is the same for both the vectors. But if you observe, magnitude is not the same. Here this is the magnitude of the first vector, but this is the magnitude of the second vector. So magnitude wise they are not the same, but they are moving the same direction. So I can say they are not equal. And now consider this case. In this case, the magnitude of these vectors, so it's all the same, but they are moving in different directions. So the direction is not the same and the magnitude is the same. So same magnitude, different direction. So here also I can say that the vectors are not equal. Now consider the last case where the vectors are A and B, which are moving in the same direction and with equal magnitude. So here the direction is the same and they are moving in the same direction and the magnitude is also the same. So that is how I can say that these two vectors are the same. So given any two vectors, this is how we can compare the two vectors depending on the magnitude and depending on the direction. So if they are moving in the same direction with the same magnitude, then only we can say that the vectors are the same. Otherwise, they are not the equal vectors. Now let's discuss in the further slides, we will be discussing various operations on the vectors. So how do you apply addition, subtraction, then the scalar product of the vectors, how do you multiply a scalar to the given vector, then what is inner product, outer product.